Assalamualaikum warahmatullahi wabarakatuh. Today we want to present uh, before we started before we start, aku bingung ayat.
Cakap ni lah, my name is cakap nama tu ya.
Okay.
Assalamualaikum, my name is today we want to present about
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hanafi bin Arifin.
my name is Muhammad Hamdi Hamzah bin Ahmad Syui.
Today we want to present the chapter DC Servo Motor System by our topic motor selection and sizing.
8.4.1 Motor selection. Motor acceleration torque or peak torque is the torque is needed during the acceleration time period. Note that the peak torque is also referred as the motor acceleration torque. Next is cruising torque. The level of torque the motor can supply continuously at cruising or constant speed without overheating. Note that at cruising, the torque developed by the motor is used to overcome the frictional torque of the system. Hence, Tc equal to Tf. In general, motor torque can be computed from the equation. Ta equal to J1 plus Jr plus Jl plus Js multiplied by A plus Tf, where Jr is moment of inertia of rotor, Jl is moment of inertia of load, Js is moment of inertia of the load. A equal to angular acceleration. Tf is constant friction or gravitational torque. The continuous torque Tc is computed as the RMS value of the required torque. Very often at steady state or equilibrium state, Tc is the torque required to overcome friction at a given speed. N equal to square root Jl divided by Jr.
The first selection approach is to choose a servo motor large enough for a machine that has already been designed. The second is to select the best available servo motor with a specific feature and build the system around it. The third is to study servo motor performance and system requirement and match the two. Find a motor and drive that match the supply voltage, has a rated speed, continuous torque, and peak torque rating that exceed the value calculated above. Look at the motor rotor inertia to find one that satisfies the initial ratio requirement for the servo drive you are using. Most of the motors available likely were capable of far higher speed than needed. Divide the motor speed by the required speed and round down to get a starting gear ratio. Then divide the required torque by the gear ratio to find the new required torque. This will narrow the choices down to just a couple of motors.
Figure 1.0 show the process of motor selection by using DC servo motor. Firstly, positional input signal. Next is amplifier for error detection, and then DC motor. Next is gearbox for speed reduction. Next is potentiometer. When error signal is detected, it go back to the amplifier. The last one is output shaft.
8.4.2 Selecting amplifier. To select the amplifier, we need to understand the effect of the torque constant Kt. Kt Newton meter per area. Motor A 0.1, motor B 0.2. Ke volume radiance, motor A 0.1, motor B 0.2. Ra pi, motor A 0.5, motor B 0.5. If the motor is required to run at the speed of 3 k rpm and produce a torque of 1.2 Nm. Motor A armature current 1A equal T per Kt. Motor A 12A, motor B 6A. Armature voltage EA equal Ke. Motor A 31.42 voltage, motor B 0.62.8 voltage. Terminal voltage Vt equal Ia Ra plus Ea. Motor A 37.4 voltage, motor B 65.83 voltage.
Therefore, for the same output power, a higher torque constant implies that the armature current is proportionally lower. Then the amplifier chosen for the above specification must be able to supply the peak current and voltage requirement. Next is peak current is required during the acceleration interval. Since T equal to Kt Ia, then Ia P equal to Tp divided by Kt, where Tp is the peak torque and the peak supply voltage is given by Vpk equal to Ke max plus IAP minus Ra.
DC reference voltage is set to the value corresponding to the desired output. This voltage can be applied by using another potentiometer, control pulse with to voltage converter or through timer depending on the control circuitry. The diode on the potentiometer produce a corresponding voltage which is then applied as one of the input to error amplifier. In some circuit, a control pulse is used to produce DC reference voltage corresponding to the desired position or speed of the motor, and it is applied to a pulse width to voltage converter. In the converter, the capacitor starts charging at a constant rate when the pulse high. Then the charge on the capacitor is fed to the buffer amplifier when the pulse is low, and this charge is further applied to the error amplifier. So the length of the pulse decides the voltage applied at the error amplifier as a desired voltage to produce the desired speed or position. In digital control, microprocessor or microcontroller are used for generating the PWM plus in terms of duty cycles to produce more accurate control signal.
Figure 1.2. The feedback signal corresponding to the present position of the load is obtained by using a position sensor. This sensor is normally a potentiometer that produces the voltage corresponding to the absolute angle of the motor shaft through gear mechanism. Then the feedback voltage value is applied at the input of error amplifier or comparator. The error amplifier is a negative feedback amplifier and it reduces the difference between its inputs. It compares the voltage related to current position of the motor obtained by potentiometer with desired voltage related to desired position of the motor obtained by pulse width to voltage converter and produces the error either a positive or negative voltage. This error voltage is applied to the armature of the motor. If the error is more, the more output is applied to the motor armature. As long as error exists, the amplifier amplifies the error voltage and correspondingly powers the armature. The motor rotates till the error becomes zero. If the error is negative, the armature voltage reverses and hence the armature rotates in the opposite direction.
8.3.8.4.3 Selecting position sensor. The principle for selecting position sensor apply whether the sensor is an encoder resolver. Selecting a position sensor depends on the resolution required. Increasing the resolution improve the system in two ways: A. Reduce quantization error. B. Smoother motion at low speed. However, increased resolution has one negative effect. It may limit the maximum speed. For example, if the maximum frequency of the controller is limited to 500 count per second and the sensor resolution is 10 passes per rotation, the maximum speed of the motor at 50 rps. The specific parameters that define the performance of a position sensor will vary according to the sensor type being selected, since the underlying technology principle just change for type to type. Some key specifications to be aware that apply to most position sensors are as follows. Measurement range. Provide an indication of the distance range for the sensor for which a measure value can be obtained. Resolution. Define the value of the smallest position increment that the sensor can measure.
Accuracy, a measure of the degree to which the measured position agrees with the actual position of the object being measured. Repeatability, reflect the range of values obtained for the measured position when the sensor performs an identical measurement over time. Linearity, the extent of deviation from linear behavior of the output signal measured over the range of output for the sensor. Other selection consideration for position sensors include the size and weight of the sensor. Second, whether the sensor provides absolute or incremental position information, the operating temperature range for the device, the sensor's ability to withstand other environmental and operating conditions, such as the presence of condensation, contamination, or mechanical shock and vibration, the ease of installation, the initial cost. Thank you for your attention and your time to hear our presentation. That's all from us. Thank you.
Thank you.